Thank you very much for the introduction, and let me start by saying that this project wouldn't exist without Hélène. First of all, it's a collaboration, among others, with Martin Lara, who is a PhD student and now postdoc with me, a PhD student from Lara and Srinivas, and now a postdoc with me in Frankfurt. And it's also building on earlier work by Hélène with Mark Shusterman and Srinivas. And last but not least, it also depends on questions asked by Hélène and her enthusiasm that was already mentioned about mathematics. So thank you. Okay, before I forget, this is really work I present, which is in joint work with Martin Lara and Srinivas, who are both in the audience, I'm very happy about. And the second part is about joint work with Piotr Achinger, Lara Hübner, and Martin Lara again. So the title already says that I'm interested in fundamental groups. So the fundamental group will be pi1 étale a la SJ1 at the moment. And finiteness properties means I'm interested in this as a profinite group, and I'm interested in whether this is finitely generated or finitely presented. And whenever I say this, I mean in this topological sense as profinite groups. So I will save several minutes by not always saying topologically finitely presented and topologically finitely generated. Yeah, so our knowledge about fundamental groups, I would say, entirely algebraically is rather scarce. There are very few varieties where we actually can compute algebraically what this group is. For example, the projective line, or products of projective lines, the projective n space, or at least two-dimensional complete intersections in projective n space. All of this can be done algebraically, and it's rather boring because it's simply connected. The next group of varieties where we know this group algebraically is for abelian varieties, or in characteristic zero, when we have Finite formula also for group schemes. There, the fundamental group is, so étale covers are all finite central isogenies, and if you understand the groups, you can compute which of them are there and get the fundamental group in an algebraic description. Why I'm saying this? Because there are examples like the projective line minus 3 points, which arithmetically have some significance because the Galois action on this fundamental group is rather strong. We have Bailey's theorem, and understanding this fundamental group algebraically would maybe shed light on the absolute Galois group of Q. So here, of course, I mean Q bar. But to my knowledge, we're not able to compute the fundamental group of this fairly easy space in entirely algebraic terms. In a different direction, a group which causes trouble is the fundamental group, let's say, of the affine line over fp bar. It's also a group, but since Finite formula in characteristic P doesn't work, we know a lot about this fundamental group thanks to the work of Monsieur Michel Reynaud on the Abianca conjecture. So we know which finite groups occur as a quotient of the étale fundamental group of this space. And I like to refer to this as a monstrous result, because if the characteristic divides the order of the monster group, then the monster is a quotient of the fundamental group here. And so this group is rather big, rather monstrous. Okay. This was introduced in order to stress that in order to have some hope of finite type properties, then really tameness is important in characteristic P. Without tameness, there's no hope to have finite generation. Yeah, and also to sort of set the challenge that although we know the finite quotients of this, so the question is, what is the étale fundamental group of this space? What can we say about it? Yeah, and also to stress a notable difference between finitely generated groups and arbitrary profinite groups. An arbitrary profinite group is not determined by the set of isomorphism classes of groups which occur as finite quotients, whereas a group which is topologically finitely generated actually is, which is kind of surprising group theoretic fact, but it's a fact, and therefore whether a fundamental group is of finite type is actually an important feature. Okay, so how do we usually know, if it's not algebraically, that these groups are finitely generated? So let's say we have K algebraically closed and it's in characteristic 0 and small enough to be embedded into the complex numbers, and we have a variety over K connected to have a fundamental group, then the complex points are homotopy equivalent to a finite CW complex. And this means that the topological fundamental group of this space is finitely presented. So FP means finitely presented. And here, the only case where this is meant in the discrete sense. So this maps into the étale fundamental group of the base change to C, and this projects onto the étale fundamental group of X itself. And this map here, by the Riemann existence theorem, is an isomorphism after profinite completion. And this guy here is simply an isomorphism because the fundamental group in characteristic 0 is geometric. And so you see, we need transcendental methods to deduce that our étale fundamental groups in characteristic 0 is finitely presented as a profinite group. Okay, so in characteristic 0, in some sense, I've done my task, and it's been done long ago. So characteristic P positive is the actual task, and there we use Grothendieck specialization. So assume we have K with a complete DVR and residue field small k, which for simplicity we assume algebraically closed, and then there's an algebraic closure in the generic fiber as well. And we also have something proper smooth over the DVR. Then specialization goes from the characteristic 0 fiber geometric to the characteristic P special fiber. And this is surjective and an isomorphism on prime to P completion. And so the surjectivity is nice because it transports finite generation, but it doesn't transport finite presentation. So finite presentation is a whole different issue. And also the structure as a profinite group, so in terms of generators and relations, is unclear because nobody knows how to describe the kernel. This is the first step, and it's basically the main link that we're going to use between characteristic 0 and characteristic P. But it has flaws, because not all varieties in characteristic P lift to characteristic 0. And so you cannot use this argument all the time. So you have to find ways around. And another problem, which unfortunately I cannot say anything about, has to do with how I started here, emphasizing that it would be nice to have an intrinsic description or method to compute this. So it would be better to have an intrinsic characteristic P way of computing these things, especially because we are slowly working our way towards rigid analytic varieties. And as we have a complex analytic way of getting a hand at finiteness, would be nice to have a direct rigid analytic way of getting our hands at finiteness. Okay, but we don't. So things have to be even more involved and roundabout in some sense. Okay, so what do we know about finite type properties from the literature? So already in SJ1, the basic technique that I'm going to explain a bit later was developed, namely some descent results, and you can get there the statement that pi1 tame of smooth curves is finally generated. Fg finally generated, and there's also, I think, in SJ7, this time it's Madame Michel Reynaud. She proved using strong resolution of singularities that if I replace the fundamental group by its pro-prime to p completion, that this is finitely presented, and happy that Fabrice is in the audience. So 2003, he removed so unconditionally. So, and I should say probably that x now is over k, which is k bar, and the characteristic of k is p positive. Okay, so the prime to p fundamental group was long known to be finitely presented, and then came the theorem by Hélène, Shusterman and Srinivas, 2022, I think, it's published, which says that x over k, k bar, characteristic p, is smooth and projective, then the étale fundamental group is finitely presented. And they proved even more. If x is quasi-projective with normal crossing divisor projective compactification, then they prove that the Tame fundamental group is finitely presented. And here, tameness is a notion which I have to explain a bit more, and will be also the topic of Lara and Hübner's talk, I guess, today. Tameness is meant in the sense of Grothendieck Moore, as in SJ1, where you ask your covers to be well, comma covers at the generic points of the components of the boundary. And I think in the paper they use that this is equivalent to curve tameness, a notion which you can learn of in a paper by Schmidt and Kertz, and I'm also happy that Moritz is here. So this is a very special talk, because many people are in the audience whose work I'm talking about. So bear with me, I hope I present your work right. Okay, let me say at least one word about this. So projective and smooth is used in order to cut down to the surface case, and then in the surface case for finite generation you can even cut down to curves, and then you lift to characteristic 0 and basically use this transcendental input. But in order to get further from finite generation to finite presentation, they make use of the work by Lubotsky, who in 2001 wrote a paper about finite presentation for profinite groups, which seems to be crucial here, because in that paper he he presents a cohomological criterion how you can see that a finitely generated profinite group is actually finitely presented. You need to have, in some sense, a sublinear growth for the second cohomology. And this is astonishing because the analogous questions for discrete groups are, I think, completely open. So discrete groups in this case are much more complicated than profinite groups. And actually, finite presentations for profinite groups that you can also learn from this paper, which I recommend to read, are fairly rigid things. So you can transform one finite presentation into another, and in some sense, then therefore, there's an optimal one. And yeah, so the world of group presentations for profinite groups is much easier than for discrete groups. Okay. I also deduce from that proving that something is finitely generated is actually much stronger than in the discrete case, because afterwards it's only a cohomological step to prove finite presentation. Yeah, the only comes in big quotation marks because this is actually the marvelous part of the paper where they use a lot of machinery and come up with an analog of a canonical extension for a sheaf in FP vector spaces. So this is really nice work. Okay. Now, how do we go from here? So I first present the result with Martin Lara and Srinivas, and I'll do this by reminding you on the method of descent for Galois categories. So maybe first the theorem. Okay, again, K is an algebraic closed field, characteristic P positive, and X over K is now proper and connected. I tend to forget connected because I'm always looking at fundamental groups, and if they're not connected, then choosing the base point actually picks a connected component. Then this is just the phi one that I'm talking about. So it's just an extra assumption that I sometimes forget. Okay, here now just a proper connected variety, and then the étale fundamental group is actually finitely presented. Right, so you get the same result, but without any regularity and without projective, right? Just quite general. Okay, how does that work? So it uses descent. So if x prime over x is just some map f, then we say that this is descent if the pullback functor that I'm going to write down now is fully faithful, and effective descent if the pullback functor is even an equivalence. Oh. So what pullback functor I'm talking about? I'm talking about finite étale covers as a Galois categories of x, which I pull back to x prime, but then I get more than just a Galois cover of x prime. I get a descent datum of x prime relative x for this fibered category in finite étale covers. So a category fibered over schemes which is fibered in Galois categories. So what is an object in here? An object in here is a finite étale cover over x prime plus an isomorphism of the two pullbacks where I have x prime and I have two maps from x double prime, which is x prime over x with x prime, and then there are 3 arrows from x triple prime, which is the triple fiber product. And so this phi, this gluing map, has to satisfy a co-cycle equation on this triple intersection.
Jakob, sorry, is there any special assumption on F to set this up, or are you just taking F to be isomorphism here?
Just the definition.
This is just the definition of the terminology, and not all F do this.
No, I'm not in that, but you're not restricting to any kind of F.
The formalism, first of all, doesn't require restricting this. Right? I have to restrict a bit because I'd like to say that this is quite generally a Galois category. Right? And this will only be true, I think, if this is surjective and maybe under some other circumstances. But surjective, I think, is okay.
Has to be connected.
Say
X prime has to be connected.
X prime does not have to be connected. You get this thing connected via these mutual intersections. So X has to be connected. But X prime does not.
But then you get a Galois category?
Yeah.
Fibers connected, no?
No, X prime does not have to be connected. Fibers don't have to be connected. Just X has to be connected. We want this to be a Galois category, so X connected. And okay. And now the statement, which is already in SJ1, is 2. So is F descent plus the fundamental group of the connected components. So for all x prime alpha in pi 0 of x prime. So this should be finally generated. And the number of connected components of x prime and x double prime are finite. Then pi 1 of x is finally generated. And if F is even effective descent, plus pi 1 x prime alpha is finitely presented for all x prime alpha as above, and pi 1 of x double prime beta is finitely generated for all x double prime beta, a connected component of x double prime, plus the 3 sets of connected components that occur here are finite, then pi 1 of x is actually finitely presented. Okay, so the higher up in the simplicial degree you get, the less structure and finiteness you need. But you need one step more if you want finite presentation instead of just finite generation. So that's quite nice. And this is well, a descent argument, but I'd like to call this as a van Kampen result. Because the original van Kampen theorem in topology is a special case of this. And so the formula how you compute the fundamental group of X out of the constituents which enter in this Galois category, which is kind of a mixture between a combinatorial one, which comes from the topological realization of pi 0 of this part of a simplicial datum, and the fundamental group of the constituents itself. Okay, so how do we prove this theorem now? So here's something where I'd like to pay tribute to the late Arthur Engel that hardly anybody of you probably know. He's a a professor in didactics in Frankfurt who used to be the coach for the German IMO team. And he told me that if you have an idea, you should not only apply it once, you should apply it twice. And it's astonishing how often I come across a situation where this is actually, in retrospect, correct. Because here, what we're doing is we're running a program where we use descent, and in order to prove finite presentation, in the first round, we just focus on finite generation. Because in the second round, when we already know finite generation and generality, we don't have to focus on the specific properties of these higher self-intersections anymore, because they have finitely generated fundamental groups already. Right? So in a first round, so apply.
It's a bit like Schiffification, but more evolved, right?
Yeah. Schiffification is another instance. They also do it twice, right? So.
Carrying off that, is it true that this is effective descent is somehow saying that finite étale is a co-sheaf in group points or something?
Well, but it's well, only for very specific f's this will be effective descent, right? So, for example, we are applying this to the normalization map. And also on the connected components of the normalization map, we do resolution of singularities in form of alterations à la de Jong. And so we may assume after these two steps that we end up with constituents which are smooth and projective.
The ground field is algebraically closed?
The ground field is algebraically closed. In all of this, you can soften the assumption on the ground field. You get a short exact sequence, and then finite type properties of the Galois group of that field enter. And this is more.
The alteration also covers the field. So
yeah, but this is no problem. Okay, so this applying twice doesn't refer to these two steps. Here you could package these together. So this is effective descent and this is effective descent. So in the first round, we are using the result Shusterman and Srinivas for these guys for finite generation. And then we get that for all proper varieties, the fundamental group is finite generation. And once we know this, we do the whole thing again, and this time we're using the second part of the criterion, and we know that these guys here are finitely presented, and the ones that we don't control, namely these mutual self-intersections, they are finally presented by finally generated by the general first round process, and so we don't care that we don't control them, and in the end we get finite presentation for these groups, right? So actually. Quite nice. I should say that most of this could have been done 20 years ago, with the exception of having this building block that for smooth projective varieties, knowing finite presentation is actually the new result by Hélène, Srinivas and Shusterman.
Well, the iteration is number one, and this is Johann.
Sorry. Sorry, that was something else.
20 or 30.
So when was alteration? That's more than 20 years, right?
I have no idea.
It's already that old. Okay, so now I'd turn my attention to Tame covers of rigid spaces. So we're shifting gears. So I'm looking at rigid spaces in rigid analytic spaces over some non-Archimedean complete rank 1 valued field. So real rank 1, and so it has a valuation ring and some residue field, and for simplicity I assume that the residue field is algebraically closed, but maybe I don't have to do that, right? So, well, at the moment I'm not saying anything here then. Okay, and then these rigid spaces, rigid analytic spaces are adic spaces over spar k plus, locally of finite type. And now we'd like to say what it means for such a space to have a tame cover. So the definition, which in more generality for the tame adic side is contained in a work by Katharina. So here we say that a finite étale cover y over x is tame if for all points y comma v, which are points of this adic space over some dominating the base. For all these, this v is evaluation on the residue field of y. So we have small x is f of y in x, and so there's a valuation v w, which is v intersected the residue field at x. And so we want that v over w is tame. So there, for every point, adic point, and evaluation on the residue field, we get an extension of valued fields. So and we want this extension to be tame. So in some sense, étale means that in the interior of the adic space, we want the covering to be étale, and these are valuations which are slightly poking their nose out of y. It's like having small carrots which sort of are decorating this in different directions, but they are not too free. They still have to dominate the spar of the base. And so this is like asking tameness for all points in favorable constant situations. This is Huber's universal compactification of y. And we think of this as adding some boundary to x and y, along which we are requiring ramification to be tame. So in the earlier result with the tame fundamental group of this good compactification, there was Grothendieck tameness or curve tameness or valuation tameness or whatever, and all these different notions of tameness agree there. And this is now a further notion of tameness, which I like to call adic tameness. And then I will delete the adic, because this is kind of for adic spaces the natural intrinsic tameness condition. And then I'd like to call this only tameness, but I always think about this as being tameness. Here's an example. So we have the unit disk, which is spar x equals spar of qp of a variable, call it t relative to zp, a variable, and the cover given by the usual Artin-Schreier equation, s to the p minus s equals t. This is étale over the formal model that this disk has. And so It extends as an étale cover in the degenerate direction, but it's still not tame. Because the adic tameness, so this universal boundary in Huber's sense, that extends towards the completion of the special fiber, and that contains the point at infinity of this projective line, and certainly this is wildly ramified there. So this is not a tame cover, right? So this tameness assumption is actually restrictive, but it's a notion which defines a full subcategory of the finite étale covers of X, which we denote by tame covers, or superscript tame, and it's not hard to see that this is a full gamma subcategory.
Do you have a specialization map here to the characteristic key? Can you define it from your notion of tameness? Or can you define it?
I think I'm going to talk about this in a minute, so I'd like to postpone this. Okay, so the theorem 2 is now with Achinger, Hübner, Lara, and myself. It says, so two cases, K could be algebraically closed, and still with the assumption, so rank 1 non-Archimedean discrete, non-Archimedean valued, or discretely valued, still rank 1, with algebraically closed residue field, and maybe secretly what we really need is that the tame fundamental group of K plus is actually finally generated. Which is true under these two circumstances. And then an X, which is a connected quasi-compact, quasi-separated rigid analytic space over spar KK plus. For such a guy, the tame fundamental group, which is of course the fundamental group of the scalar category of tame covers, this guy is finitely generated. Yeah, finally generated in that generality. If we have a semi-stable global model, I mean, not just locally a semi-stable model. I meant just really this guy is has a semi-stable formal model. Then I think we get finally presented. Right?
X is not proper here, right?
No, X is not proper.
So when you say semi-stable, you mean also with a good horizontal compactification?
Yeah, yeah. And this is still work in progress. We hope to improve it, right? Because of course we would like to have finally presented here in all generality, but there are certain steps in the proof where finite presented doesn't go through. Finite generation goes through, but finite presentation does not so far, right? So part of that is still work in progress, right? So the result might improve over time. Okay, so how do we go along proving this. First, we are making use of descent techniques, so these Van Kampen techniques, and they allow us to pass to a finite cover by an open covering, and then as a second step we can then pass to something regular. I should say that there's also a part where we replace K by its algebraic closure and completion. And then this regular is even smooth. And here we are making use of Gabor uniformization. And it's a bit involved. I don't want to go into this. And as a third step, we're using the existence of formal semi-stable models locally, which is a result by Temkin. So there's some heavy p-adic rigid analytic machinery going in there. And all of that now reduces to the case that, that there's a formal model over K plus, and also a special fiber over small k. And suddenly, these geometric objects should be equipped with a log structure. From the special fiber in this thing. And the big caveat here is that this is not Fs. So we are forced to do some logarithmic geometric exercises in the world of non-Fs saturated log schemes. Okay, let me clean a board. So the proposition which addresses your question, Hélène, about specialization is, I think, the following. So here's a diagram of Galois categories. So we are, with that notation, the finite covers of X, they contain the finite étale covers which are tame at the generic points of the special fiber. And this turns out to be equivalent to the finite Kummer étale covers of this formal scheme, which are equivalent to finite Kummer étale covers of the special fiber. And this equivalence pushes down to an equivalence of the Tame category here, finite Kummer étale of Esnault of tameness. So this is equivalent. So in fact, the category that we're interested in here, this one here, can be described entirely in terms of a category of tame covers of this special fiber, which is now a variety of an algebraically closed field, at the cost of having a log structure, which is not Fs, and tameness is also meant in this adic sense. Now for this discretely ringed case, where still this space of additional points with valuations can be defined and gives you kind of a compactification of this thing in terms of lots of valuation rings where étale covers or the underlying maps under these comma étale covers, they should be tame with respect to this collection of valuations.
What's the relation between that tameness and tameness with curls or in geometry?
So it typically sits somewhere in between, but in the good cases where you have a good compactification, it's equivalent, right? And
but you know it's actually different.
Do we know examples? One is. Do we know examples where things are adic tame but not curve tame?
No, because that's equivalent.
Oh.
No, in all cases?
For curve tame, yes.
Oh, okay.
Or well, maybe something non-Euclidean. Yeah. Then yes, because then the notion of a curve becomes degenerate in some sense. But for Euclidean schemes, or yeah.
Okay, thank you for the question and the answer. Okay. Yeah, let me drop a few more names here. This equivalence you could view as some log purity or some non-Noetherian Bianca lemma. That needs to be proved, and an important process here is that of eta normalization. Where you normalize in the generic in the structure sheaf of the generic fiber your formal things. Okay, do I have time for this? Maybe I postpone this if there's more time. Okay, so now we have transferred this into the log world, and what we then, of course, need is a theorem in the log setting. So again, Achinger, Hübner, Lara, and myself. K is algebraically closed, characteristic P positive, and X over K is a log scheme. I probably have to say what type of log schemes and log structures we are looking at, because here in my notes it says log schemes of type VDiff, and that says nothing to you because I skipped a sheet. Okay, so these log schemes are not that bad. They have étale locally charts, but the charts are not by fine saturated log monoids, but just saturated log monoids. And that makes things a bit more difficult because you don't have finite type. But there's this VDiff, which is in analogy to important results by Bosch-Lütke, Bohm, and Reynaud in the rigid analytic business. It means that these monoids, they are not too far away from a monoid which is both divisible and valuative. So divisible is clear, and valuative means that for every element, either in the groupification, either the element or its negative is in the monoid. So like the positive elements of a value group. And apart from that, these are saturated in a finite presentation over such as monoids. So the monoids on which we build the charts. And well, finite presentation, and then there's a saturation step, right? And the saturation step itself might not be of finite presentation, right? And I should also say that there is work by Bogdan Savialov and by, no, I will mispronounce, Hongsheng Diao and Xizhang Yao about generalizing log schemes, FS log schemes in this direction, which also deals with similar questions. And yeah, so this is what underlies this type V diff. This is the type of log schemes which occur as special fibers of such a situation, because there's this non-FS part of the log structure coming from the value group downstairs. Apart from that, it's finite presentation. Yeah, but there are certain technicalities which then have to overcome. Okay, but this should be a connected, of course, log scheme, and then it says that the tame fundamental group of such a guy is finally generated. And here I mean this as a log scheme, and this is of course then the fundamental group of the finite Kummer et al. Covers, which are also tame in this adic sense. Okay. Of course, given this equivalence, this proves theorem 2. And so now we have to prove this statement. And here we are use that such an X has a log stratification. And this is locally finite. So in this some finite type thing I should have asked. Okay, so let's say this is a finite log stratification. And we're doing Noetherian induction by always adding a last open cell on which the log structure is locally constant. So we have an open where the log structure is locally constant, and this is a closed where we already know the statement, and then we're using also the completion T of X along Z, and in there kind of T0, which is the intersection with this open, and we need to prove a descent statement for this as a covering. So tame covers of X can be restricted to tame covers of U, and somehow also to tame covers of T, which is equivalent to tame covers of Z, and then they need to be glued along tame covers of T0. And I think everywhere I have to put in a K for finite Kummer et al. Okay, and this should remind you on Bouville Laszlo gluing. And we get away with something slightly cheaper because at the moment we are only formulating this as finite generation, so we don't have to control this as an adic space too much, and we can still deduce that this as a Galois category is contained as a full subcategory into a Galois category constructed out of this upper part of the diagram, and then we can deduce from finite number of connected components here and our result in these two steps also finite generation of fundamental group here. Okay, and that leaves us with the task of doing the start of the induction, which is in some sense the case where we have a locally constant log structure. So locally constant log structure. So then an X maps to, this is the underlying scheme, epsilon. We have a homotopy sequence, which here, let's say we have a point in here, and we have a chart based on a saturated monoid which is type V-diff. And then here we have the fundamental group of that monoid, which is just the HOMS of P groupified to Z hat prime 1. Still in characteristic P, so the prime deletes the P part of that. And since this is saturation of finite presentation over something divisible, this P group, although it's huge, it has a huge divisible part which goes to nowhere here. And so therefore this is finite presentation as a profinite group. And then from this homotopy sequence, which is very easy to prove, we get that finite presentation, a finite generation here is equivalent to finite generation here.
What is C prime hat? What is a prime?
The prime means removing the P part.
Ah, you remove P, okay.
Yeah. Okay, so that reduces to theorem 4, also HLS, 224. Okay, algebraically closed, characteristic P positive. X over K is a connected variety. And then pi 1 tame of X is finally generated. Right, so this is the last guy that needs to be shown finite generation. And here this tameness is in fact adic tameness, because we're not making any assumption on having a good compactification, right? But the proof, of course, is again, as in the proof by the result about proper varieties with Martin and Srinivas, you're doing normalization and alteration to deduce this from the analogous theorem for smooth quasi-projective varieties. And that brings me back again to Hélène's result with Srinivas and Shusterman, and that completes the proof of this, and going back and back, also the proof of this main result. Thank you very much for your attention.
Thank you very much. Are there any questions?
So I just want to ask a very naive thing. So here you mentioned this Boole-Wallace law, but if I remember correctly, this thing is somehow in the coherent mode. So how do you compare with this law?
This is only as an analogy, right? But in some sense, these guys are built up from coherent algebras. And so if you can do coherent descent, then you can, which is compatible with tensor products, and you cook up coherent algebras, and then you need to check étaleness and comma étaleness. So that's the most important part.
Can you say something? So if you wanted to get finite presentation in general here, like what steps would you need to improve?
I mean, given the diagram you gave us from, here it's finitely generated and above finitely presented, above finitely generated, it's enough to see down this finitely presented, but here you have many more steps in, yeah.
Well, there are two strategies. Either you go through this proof and you see at which cases the descent statement isn't good enough yet, right? So whenever that occurs, if you can jazz up from descent to effective descent, then you get a von Kampen formula, which, given the ingredients, actually gives you finite presentation, right? So that's a viable route, but there's this. Yeah, so maybe a word of warning is that much fewer maps are actually effective descent in this setup, because if you take the Artin-Schreier cover, that's not an effective descent map anymore. Because if you take the Artin-Schreier cover itself, you put it back, it splits. So on a split thing, the the gluing is tame, but it doesn't descend to something tame, right? Actually having effective descent statements is much more complicated. There's the second route where you resort to the cohomological criterion and you try to bound H2, right? And I said if you have semi-stable formal models, then you get finite presentation. So if you didn't know this, then the follow-up on saying that you need to bound H2 would be that for curves we have it, right? Because then bounding H2 is not so difficult. But yeah, so this is work in progress. Thanks.
So given a sufficiently nice regional space, I can just give it to you. You can write down the finite presentation.
Oh no, not at all. Sorry to disappoint you.
Same with varieties.
Yeah. It's. I think the fundamental group for a variety is a very difficult invariant.
So the non-FS things come from the variation ring.
Right.
Can you say a few words about how shrinking and gather enter this picture?
Oh, I think
it's too long.
Yeah. Okay. Sorry.
Is there any place where Fujikawa's purity is used?
I think it comes as an inspiration here, but we have to redo certain things or adapt it to our situation, right? Because things aren't FS. Yeah.
I'm not sure. I'm not sure you said it or maybe you didn't. Do you have an F-shed theorem for? Can you deduce it from your finite generation? Once you know it's
finite.
Yeah. You will need to hit only finitely many generators. So because that might have applications.
Yeah, we should think about this. Thank you.
So it's correct that even if X is proper, despite one Tame, it's generally a smaller quotient than the fundamental group itself.
What was the question?
The question is, if X is proper, is by one Tame the same as the whole by one? Not the
No, because you have also the horizontal direction.
Yeah, you have at least tameness along the special fiber of some model, in case you have a model. Yeah.
That's why I was asking you the question about the specialization. Yeah.
There is coffee waiting, and we resume at 12. Thank you again.